Hello, my name is Mark Dannemiller, and today I'm here to talk about my project, which is a speed controller for a small DC motor using the L393D H driver. This circuit has 4 states, one for 0% duty cycle, one for 40% duty cycle, one for 70% duty cycle, and one for 100% duty cycle. It uses the ATMega328P or the Arduino, which sends a PWM signal at 250 Hz to the H driver, which then runs the motor at the specific duty cycle that is required. If we look over here, you can see that the ATMega328P runs at 16 megahertz, and for this circuit we are sending a PWM signal of 250 Hz, which is 250 PWM cycles per second. So in order to calculate the cycles per PWM cycle, we just take the total number of cycles that the Arduino can execute in 1 second, and then we divide it by the amount of PWM cycles we need, which gives us a final number of 64,000 cycles, which for the 40% duty cycle and the 70% duty cycle are these corresponding cycle values, which are just 40% of 64,000, or 60%, or 70% and 30% for these 4 values. One thing to take note of about this circuit is that it actually keeps track of the button state. So for example, if I hold down this button right here, you'll see that button flash and then nothing happens, and then it'll go after I release the button. That's to make sure that I don't accidentally cycle through a whole bunch of different states while pressing the button. Alright, now on to an analysis of the circuit. There are 3 main components, one being the integrated chip, or the L293D. Now the one pictured in my circuit diagram is the L293 and not the L293D, and for that reason I will be highlighting the components that I am referencing in the actual circuit as I talk about this one on paper. So first off, there's the 5-volt connect from VCC of the ATMega328P that connects to VCC1 and VCC2 of the L293D, and as well as the input 4A. The ground pins are connected to all 4 ground pins on the L293D, obviously the ground on the ATMega328P, and the reason that all 4 ground pins are connected is so that the heat dissipates from the chip, because this chip generates a lot of heat. The ground pin is also connected to 3A. Now 3A and 4A are the inputs for the IC chip for this motor. And normally the chip can switch directions if the 3A and the 4A pins were swapped, but in this case they're both fixed to 5 volts and ground respectively. Now 4Y is connected to the positive or the positive counterclockwise lead of the motor, and 3Y is connected to the negative or the negative for the counterclockwise lead for the motor. Capacitors are connected to 4Y and 3Y in order to deter back EMF from the motor, and I'll include an instructable link to the L293D tutorial where I found how to connect these capacitors, and the person that made that has a really good description. Now for this chip, we have port B bit 2, or digital pin 10, which is connected to the 3-4 enable, and that is where the PWM signal will be sent to this chip in order to determine at what frequency to operate this motor. The second part of this circuit is just a push button connected to digital pin 2, or port D bit 2. And the third part of this circuit is this debug LED here, which is connected to digital pin 0, or port B bit 0 in the ATMega328P. Now to talk about the code for this project. As I stated before, this project is using assembly. Now, obviously, when using an Arduino, C++ is a much better option, but in this case, we're programming to the ATMega328P directly. So we're using Microchip Studio, and this is how we are programming the circuit. So first off, we set a few values for our 40% and 70% duty cycles. Now, these values will be implemented into loops later on in order to get this 2599 cycles and 38399 cycles, which come from the math that I showed earlier. And as you can see, this is one cycle off each. And the way that these values here were calculated for the loops were through this Python script right here, which basically just takes the amount of cycles that we want or that we desire, which is this 25, 600, 3800, all these values here. This Python script takes those cycles and it tries to find several values that will fit into the form of this loop right here that will attain the desired delay time that we want. Because these two loops down here, which are the off and the on loops, are the delay loops that happen in between our PWM cycles. So after we declare those values, then we initialize the stack pointer, and we also initialize the input-output pins. So for example, we set the second bit of port D to an input, which is digital pin 2, and that will be for the push button. We also activate the pull-up resistor on that button so that we don't need to have a resistor in our circuit for the button. And this also means that this button is an active high, so whenever we're detecting the push state of the button, it will be a low and not a high. All right, we set the digital pins 0 to an output for the debug LED, and we set the second bit of the B port, which is digital pin 10, to an output for the purpose of controlling the motor on that PWM band, like I said. We also use register 16 and register 17 in order to keep track of a mode, which is R16, which we're going to use in basically a switch later on. To keep track of mode 4 is going to be our 0%, mode 3 is going to be our 40%, mode 2 is going to be our 70%, and mode 1 is going to be our 100%. And then we also use R17, which holds the button state. It basically only switches whenever the button is pressed or released, so that way we don't accidentally switch through states too fast. So here is the code right here, or this is the main loop of code. So first we're going to disable the debug LED, and then we're going to check for a button release. So basically this R17 should be 0 in the first place, and so it's going to basically check if we have a cleared bit on pin D, or sorry, it's going to check for that, and if we do have a clear bit, then it'll skip this instruction, and if not, then that means that our button is in release mode, and so it will just automatically set this register to 17. So then it'll check for the opposite state, which is it will check if we're having a button press. If it detects a button press on that pin D at the time, then it will call this subroutine, which is button press. And if you notice, we kept track of whether or not we are in a button press currently using this R17. So down in button press, it's going to first check if we're pressed. And if we're already pressed, which you notice this line of code right here is the only thing that will set the state to be pressed. So if we were already in that state, then it's just going to automatically return out of this subroutine without executing all of the code in there. And this ensures that this code only runs one time whenever we press our button. So for example, it'll be set at 0 in the beginning, and then when we detect a button press, it will call button press, and at this point, this R17 will still be 0, and so it'll be able to pass this chunk of code, and it'll then set the button state to 1. So after it sets the button state to 1, it's going to set that debug LED to show that we're currently running this subroutine, and then it's going to check for the current mode of our system. So if we're in the first mode, then that means we're going in an order here. So if we were in mode 1, then we would want to jump over to mode 4 for 0% next. So in this case, if we're in mode 1, then it's just going to jump all the way down to this next line down here, which it will decrement the mode to the next state. And in this case, if we were in mode 1, then that decrement would then lead to a 0. So this BR_NE here will check if we get to a 0, and if we are at 0, then it'll reset our state of our motor to 4. So that way we loop from 1 to 4 to 3 to 2 to 1 over and over again. And if it's not 0, then this instruction here will be skipped, and this instruction here will be skipped, and we'll just return back into our main loop of code. So that's for the case of 1. Then for the case of 2, which 2 is going to be this one right here. So if we're in 2, then we want to go to our 100% state. So in case of 1 and 2, it's going to skip to next. The reasoning for that is because only if we're going to our 40% or our 70% do we need to LDI values. Now, there were several ways that this project could have been done, and one of those would be to have 4 subroutines, 2 for the on and off of the 40% and 2 for the on and off of the 70%. I opted to just change what these R25, R26, and R25, R26 values would be here. Oh, and R27 and R28 values. If we were in 40% values, then it changes it to the 40% values that we declared at the top of the code. And if we are in our 70% values, then it switches to the 70% values. And so these states right here are basically the equivalent of a switch in C, if you're familiar with a switch in C. And if none of these 1, 2, or 3 are caught, then obviously our mode is 4, and so it'll run the switching to the 40% values, and then it'll just rjump to next. So it'll determine what values to set based off of this switch, and then it'll just go to next and run that code that I talked about a second ago, determining if our mode was at 0 and setting it back to 4 or whatever. And the last part of this subroutine is then just calling a slight delay, just a 0.25 second delay. And the purpose of that is just so that our LED will shine for 0.25 seconds, so that way we can see and debug whether or not this subroutine was running. And then I guess I basically covered these 2 subroutines earlier, but yes, they're just delaying the on and delaying the off in our PWM, so that way we get a rising edge for the on, and then we get our falling edge for the off. And these 2 subroutines in total will create that delay time, which gives us our 250 hertz frequency to run that PWM signal. So that is what happens in button press. And then after button press happens, or even if button press doesn't happen, then it's just going to run the rest of the code. So at first it's going to check if we're in state for our 0%. And if we're in our 0% state, then it's going to skip the delay code for sending that PWM signal, and it's just going to go straight to setting our motor to the off position. And then so that way it'll just run up to begin, and then it'll just keep doing that if we're in our 0% duty cycle, because we don't need a delay for any purpose. If we're not in 0, then we set the motor on for all of the 3 other states. And then we check if we're in our 100% state. If we're in our 100% duty cycle state, then it's just going to go straight back to begin. So then this chunk of code here is the only thing that will run the entire time. It's just going to keep running and wait for a button press to send it into the next state. If we aren't in our 0% duty cycle or our 100% duty cycle, then we are in one of the other 2 states where we do actually need to have that delay happening. So at the moment, our motor is on, so then we're going to delay for on for however many cycles that is determined by the 40% or 70% duty cycle. And then we're going to turn our motor off, and then we're going to call our off delay. And then we're going to turn our motor off one more time, and that's just because it needs to be able, this code right here needs to be able to jump to something that turns the motor off, and so that has to be done down here. So that's a slight, it's a wasted instruction, I would say, but it's necessary for this switch to work. And that concludes all of the code explanation for this project.